So I'm back here. I'm on Alternator here, guys. Made a brief description of operation video of it there, I don't know, a week or two ago. And there was one major point of consideration that I completely ignored in the discussion of the alternator. As some of you guys will be well aware from your basic electricity manual that the American Navy put together 1953 or 54. Everybody has a copy of this, of course, because it's probably the best basic electricity book ever written, in my opinion. There's a couple of different ways you can actually affect or alter how much power, how much voltage and current you can pull from an induction system, which of course this is, right? We have the field coil. As it rotates, we regulate the amount of voltage, hence current, that goes through the field coil, how much magnetism it will actually generate, the intensity of the magnetism, the pole pieces, altering it between north and south as it rotates inside the stator windings here. That regulation, of course, coming from the voltage regulator itself within the assembly, will actually affect how much power output the alternator itself will actually have. We monitor the state of the electrical network in the car itself in order to know whether we need more or less generation, right? So the voltage regulator, again, will either up the intensity or lower the intensity of the magnetic field in order to meet the demands of the vehicle itself. That's it, right? That's what I said. That's all there is to it. No, that's not all there is to it. One thing that I didn't mention, guys, and it's a major consideration clearly, is, so we mentioned that this rotates. Well, this is not a constant speed drive, of course, right? It's not a CSD arrangement, which is a concern if you're dealing with the AC, because that'll affect the frequency. But this is being driven at engine speed minus the ratio change from the drive pulley, of course, right? So this probably varies in drive speed from, I'll take a guess, I don't know what the ratios are, guys, but it could probably vary between, let's say, idle speed, if it was direct drive of the car, 750-ish to 5,000, 6,000, 7,000 RPM if you're overspeeding the engine into the red line. So there's a massive speed change consideration that we need to take into account. So again, just back to the book here for just a minute. So what can actually alter how much voltage we can generate in a generation system? Well, the number of, or the length of the wire, of course we loop it to maximize the number of, we coil it in order to maximize the number of turns, the maximum length that is being cut by a magnetic field. That will affect it, of course, as opposed to a single loop. Multiple turns of the wire is going to up the amount of voltage that we can pull. And the other item is the strength of the magnet. Well, from last week's discussion, we know that we can alter the strength of the magnet coming from the field coil, an electromagnet, of course, by regulating the amount of voltage and, of course, current that we apply to the field coil via the voltage regulator, again, based on the demands of the car. But again, what about the speed changes? If we increase how quickly we pass that coil of wire across a magnetic field, cut the magnetic field, that's going to affect how much power that we can generate as well. Again, I'm using the term power for voltage and current, okay? So the faster that we cross the magnetic field, the more, the slower, the less. So we have to have some kind of mechanism, some kind of consideration for the speed changes. So how do we do that? Do we sense the speed somewhere of the rotation of the alternator? Well, I suppose that would be one way. Perhaps some sophisticated alternators do that, but this is internally regulated, guys. And can you imagine that if it's slower, the output will be lower, the lower output will be sensed downline in the network side of things. And what we can do is we can alter the amount of field current that is being applied to the field coil in order to generate more power to meet the demands. Higher speed of rotation, the voltage output would go up. We can lower the amount of field coil current in order to reduce the amount of reduce the intensity of the magnetic field, which is cutting across as it rotates, which is cutting across the stator coils in order to regulate the output. So this is a major consideration that I didn't discuss, right? And I said, you know, larger magnetic field, more output, smaller magnetic field, less output, that's all there is to it. Well, that's not all there is to it, guys. That was an error on my part, an oversight, a major oversight on my part, to not mention that the speed has a major influence on just how much power the alternator can actually can generate. So let's hook up the scan tool. Let's go to the car, one of the cars, and we'll take a look to see if the scan tool can give us some insight into how is this exactly regulated with respect to speed. Okay, so I've got actually three parameters, three PIDs on the screen here, guys. I have the engine speed, because again, the whole point is we're trying to correlate generator rotational speed, field coil rotational speed, with the generator field duty cycle. Now keep in mind, as I had mentioned in the introductory video about the alternator, it is duty cycle controlled. Okay, so in a simplified way of looking at things, the lower this duty cycle, the less field coil current, voltage and current is being applied, right? So the smaller the magnetic field. The higher this number, the greater the voltage and current being applied to the field coil, and the greater the magnetism and the higher the output of the alternator. I hope that makes sense. So again, this is directly correlated basically with the alternator output. You can look at that in an even more simplified way. So of course the battery voltage is being regulated by the voltage regulator, of course. And again, the point to this being is, how can we correlate the field coil control as it's based versus the rotational speed, which is obviously this is engine speed. Again, guys, I don't know the pulley ratio from the crankshaft to the alternator. That will be, I'm guessing that the alternator is actually rotating significantly faster than the engine, judging by the pulley sizes, right? Okay, so I guess there's two ways we can look at this. We have an idle speed right now of, you can see here, idling around 640-ish. Well, I guess it's up here. There's more accurate. So this is obviously the a graphical display, guys, with the absolute value being in the discrete value here, right? Again, engine speed, RPM, battery voltage, and duty cycle. So the point being, when the car is running, of course, guys, we want to try and regulate somewhere near this value. It'll alter a little bit, but it's trying to achieve the optimum voltage. It's plus 30 degrees today. It's actually pretty hot, and that has a small influence on the or not, maybe not so small, but it has an influence on the voltage regulating point of regulation. Okay, back to the basics here. There's two ways we can look at this, right? I can change the load. Look at the alternator duty cycle there. You can see it's hovering somewhere around 40%, right? Let's just change the load a little bit. Just off out of frame there, I'm going to turn up the fan speed a wee bit. So I'm going to increase the load on the alternator, right? I'm just going to turn off the AC there, guys. I don't want that kicking in and out. So let's go back and get a baseline. Still somewhere around 40, right? That's fan speed 1. This is the manual AC, so I can control directly the fan speed. 2, 3, and you can hear it there. So you can see the voltage is being regulated somewhere around the 14 volt point, but you can see that we're actually increasing the duty cycle. Again, we're controlling the amount of voltage and current that's being applied to the field coil, depending on how much demand we're putting on the system. take a look at the RPM, right? It may drop momentarily. I'll put on the full load up from the fan here. It does drop momentarily there. You'll see it'll regulate back down a wee bit as I've dropped the load. This has nothing to do with the alternator, guys. This is an electronic throttle control system. It'll look for the desired idle and change the opening on the throttle plates in order to try and maintain a desired idle, of course, right? So again, full load. You maybe see it just drop momentarily there. But that's also a function of course, as we increase the load on the alternator, the load is going to go somewhere. The power is coming from somewhere, and of course it's the crankshaft. So the crankshaft is being loaded up. That's why it's altering the RPM slightly, right? Of course, the voltage regulator is doing its thing and keeping us, assuming it's functional, which it is, it's keeping us close to the 14 volt mark-ish, 14.1, 14.2-ish, right? Okay, so I think that demonstrates the point about the load, right? The load is obviously going to, at a fixed speed, which is the idle speed here, we're going to have a significant increase in field coil current, voltage and current that's applied to the field coil. Again, it is duty cycle controlled, guys, so the voltage itself is not actually being altered, it's just being chopped. So, but the effective voltage is changing, which of course is changing the field coil current, right? So I think that makes the point about in a fixed speed situation, there's going to be massive changes in the generator field duty cycle in order to accommodate the load changes. So now let's just increase the RPM here, right? So this is going to auto scale here, guys, so just keep that in mind. Let's maybe go to less of a target value of let's say 2000-ish, 22. That seems to be a good point from where my foot is, 2200. And you'll notice that the field duty cycle has dropped significantly. Why is that? That's because the alternator is rotating faster. And as we saw in the textbook there, one of the things that will influence how much power you can pull or induce in the stator coils is how fast the magnetic field, the field coil, is rotating and inducing that power into the stator windings. So you'll see there's a significant reduction in the duty cycle. Why? In order to maintain the voltage at its regulation point. Let me increase it a bit even further. There's a point here, guys, where it's like the diminishing returns. You can see there's not a significant change there between, you know, almost double the RPM. Well, no, really. Went up by a third, but there's not really a significant change. But there certainly is a significant change between idle and 2200 RPM. Okay, so one more time I make the point. Check the engine speed. Look at the field duty cycle. In and around the 40% mark in order to maintain 14, let's call it 14 volts for simplicity, right? Let's up the RPM. Let's call that 2200-ish, guys. Again, the 14 volts, and you can see the field, the generator field duty cycle significantly reduced, meaning what? Reduced field coil voltage and not voltage, but effective voltage and current. The magnetism which is coming from the field coil rotor itself is being reduced because we're inducing more at a higher speed, effectively inducing more power at a higher speed and able to maintain that 14 volts in the system, alternator output. Okay, I think I've dragged this out for probably too long, guys, but I hope this makes the point. There is a significant, it's physics, there is a direct correlation between rotational speed of the alternator and the voltage regulator on the alternator is going to alter the field duty cycle in order to maintain reasonable output from the alternator over the range of speeds that the alternator is being driven. Again, keeping in mind there's obviously a speed ratio there between the crankshaft and the alternator. Okay, I've droned on for long enough. I hope this makes some sense, guys. That's it. Cheers.